for Asteroid Day here in Luxembourg. My name is George Schmidt. I'm the chairman of the Asteroid Foundation. It's a very young foundation, about 1 year old, founded 22nd of June last year when we got our papers, I believe. So again, I'm the happy chairman of that group. The Asteroid Foundation has its principal goal to educate and create awareness among the general public about asteroids and other celestial bodies, comets and the moon, maybe, or the moons, I should say. So that's our goal. Now, of course, having all these nice goals, you need lots of good people to help you out with that. And some of them are up there. First of all, our co-hosts, the Center for Security, Reliability and Trust of the University of Luxembourg is co-hosting with us today. And of course, Arend, who is graciously putting these premises at our disposal for this afternoon's briefing. I would also like to thank our premium sponsors, SES, Space Resources.lu of the Ministry of the Economy, who has been a big supporter this year again. Tomorrow Street, which is a joint venture between Vodafone and the Luxembourg incubator called Technoport. The Chamber of Commerce, and then, of course, SES and the BCE Broadcasting Centre Europe, a subsidiary of RTL Group. And last but not least, B612 Foundation, who I think has really been instrumental in putting all these events up. So again, today is our very first day of a 3-day event program. And it's about, what's going on in the asteroid science and technology. We have lots of interesting people among us, and I will not do the introduction. I leave that up to another one without whom Asteroid Day would not happen here in Luxembourg. Danica Remy, she is the co-founder of Asteroid Day, of the Asteroid Foundation, and she's the president of the B612 Foundation, our West Coast partner. Danica?
Hi, everybody. Welcome. I'm so delighted that you could join us today. We're really excited to be able to bring all of these different asteroid experts here to Luxembourg. As George said, we've got a couple of days of great program activities. Tomorrow we'll be broadcasting live from the BCE studio worldwide. BCE, along with SES, is providing us the opportunity to stream for 48 hours all around the world, really stellar asteroid content. 6 hours of that content will be live from Luxembourg. And so everyone here on the panel today will be doing much shorter presentations live from the studio at BCE. On Saturday, we have a meet and greet with astronauts at Cirque Cité, and then Saturday evening, we have our Asteroid Day Gala event. I'm going to walk you through our program today. So I'm going to hand the mic over here to Rusty Schweickart, who is also one of the co-founders of Asteroid Day, along with an astronaut and a remarkable individual. We'll have a session with Rusty, Ed, and Mark Boslough. Then we'll take a quick 15-minute break. The restrooms are down the stairs 2 floors. There'll be no coffee or tea unless you grab it really quick. You cannot bring any drinks into this beautiful auditorium that Arndt has provided for us. Then we'll hear from Dr. Fitzsimmons and Doran, and then we'll have a nice reception next door with wine and beer and juices. I'm going to be whisking away Ed, Mark Boslough, and Alan for a global press conference. So they'll be departing, and you won't see them again after this presentation. And then I'll come back down and grab folks who are going to be going back to Sofitel, where many of our speakers and guests are staying. So that is our program for today. I'm really delighted to have all of you here. So happy to have Luxembourg as a home for everybody who wants to think and love and learn about asteroids. And so now I'm going to hand it over to Rusty, who's been thinking about asteroids for a long time and is quite passionate about them. Rusty?
Hello, glad to be here. Again, I'm Rusty Schweickart. I flew on Apollo 9 back in 1969. And I'm going to be introducing the remainder of the panel. I'll give each of them a bit more of an introduction as they come up, but looking from your left to your right in the order they'll be going is Ed Liu, Mark Boslough, Alan Fitzsimmons, and Doran Pranariu. And each of them will have a different aspect of the whole issue of planetary defense and near-Earth objects or asteroids to talk about. Just as a bit of background, I'll save my comment about Ed for later, but let me just say, on second thought, but let me just say that I flew way back in 1969. I was one of the early Apollo astronauts, and I flew the lunar module for the first time. One of the interesting little episodes that occurred during my flight, it's a little bitty thin route way out on the end of the root ball of asteroids for me. Looking down as we went over the night side of the Earth, I think we were the first crew who were looking down together with all the lights out in the spacecraft because we were dark adapting for an experiment we were doing. And so our eyes were quite well adapted. Nighttime is only 45 minutes, so you really need to put on a mask and everything to start adapting early. But toward the end of the night pass, we were looking down, and finally one of us sort of somewhat tentatively said, "I thought I just saw a flash down there." You know, you don't want to say that kind of thing, right? But one of the other guys said, yeah, I did too. And the next thing, all three of us said, yeah, we saw these little flashes going off. And then, of course, it's like, duh. Of course, that's an asteroid that just burned up in the Earth's atmosphere below us. And, of course, then the next logical conclusion is, oh, it came by here on the way down, right? So that was sort of like a little bit of an awakening on a different perspective of asteroids burning up in the atmosphere. But shortly, not shortly, but a few years after my flight in the mid-90s, NASA began the astrobiology program. And astrobiology is basically the big question of how did life start, where did it start, where is it going to go, everything about life in the cosmos, including Earth. But in the Earth environment, more how extreme can life be in an environment, looking toward what kind of environments, even though they're extreme compared with the Earth, might still support life at those limits. And so astrobiology was a very, very interesting. I became quite interested in it. You don't become seriously interested in astrobiology very long. Role that asteroid impacts and comet impacts had on the early Earth, including providing some of the hydrocarbons as well as water and other essential elements for life to actually gain a foothold on Earth. So interestingly, in some sense, the first identity of asteroids and comets with life is an enabler. But of course, once life started on the planet, then they become a destroyer. So it's this very interesting yin-yang element to the history of asteroids when it comes to life as we know it. And life as we know it probably, or life even as we don't know it, has probably started in many other places in the universe as well. We know now today, as we did not at that time, that just about every star has planets around it, even binary star systems or trinary star systems for that matter. So there are many, many planets and there is around the stars, and it appears not just through modeling and speculation or theory, but also beginning now today in terms of actual data, which indicate that in fact the existence of comets and asteroids is in all likelihood a very common phenomena in and around any star that's formed with planets. So we're finding then that asteroids have played in our own case and likely play in other cases a very essential role in the creation and continuation of life on Earth. However, we also know from our own Earth history that the dinosaurs and 70% of life were wiped out in a major asteroid strike on the Earth 64 million years ago. With the dinosaurs getting wiped out. And so it's very clear from both knowledge of that event geologically and anthropologically, but also just looking at the impact rate on the moon, other things, we can easily tell that in fact life itself is I won't say tenuous because we've been around for quite a while, at least in our sense of time. Of course, the dinosaurs got wiped out. Think about it for a minute. If the planet Earth began January 1, midnight, a year ago, and this is December 31st, approaching midnight, the question is, when is it that the dinosaurs got wiped out? I can ask you to make a guess mentally about that. I won't take the time to take a poll, but it happens to be the 27th of December. So that's just an event that just happened. I mean, we think of dinosaurs being back at the beginning of the Earth. No, not true. So this is a continuing thing, and Ed and I and other people got very interested in the fact we were discovering more and more of these near-Earth asteroids, ones that come by the Earth, and the question was, what do we do about it? No one was doing anything, so we said, can anything be done? And if so, let's get it started. And that's what started the B612 Foundation back in 2001 and 2002. So I'm going to go ahead while I'm up here and introduce Ed at this point. He'll go a little further into some of the work that is currently going on. One of the things that we've realized is that indeed, with the organization we started, we have the technology which can enable us to both predict impacts and to prevent them, but we need to demonstrate preventing. And we did, for 10 years, essentially come to a pretty full understanding that this could be done and what has to be done. But one of the other things we came to an understanding of is the criticality. You can't do anything about what you don't know about. And so the really important thing, often quoted a friend of ours, Don Yeomans, who headed up the NASA program for quite a while at JPL. And Don was very fond of saying the three most important things about asteroids are find them early, and find them early. And so B612 Foundation, after spending about 10 years in figuring out that yes, indeed, how to, and yes, indeed, we could deflect them if we do find them and predict an impact, joined that most important precursor, in other words, find them early. And Ed's involved as the executive director of the Asteroid Institute related to B612 Foundation in a whole process today of innovative ways in which to find them early and know where they're going and what they're doing after that. So I'll turn it over here to Ed. And I'll give everybody a bit of an introduction in turn. Thank you. Yeah. You want to stand up or sit? I'll sit. Okay, we can all sit.
Okay. Thanks, Rusty. I guess it's up to me to move it up. There we go. So first off, thank you very much for the invitation to come speak today. I'd like to tell you a little bit about what we're doing at the Asteroid Institute. And how's that? Okay. So I like to think of our work at the Asteroid Institute as being a little broader than simply preventing asteroids from hitting the Earth. I mean, I think our roots as an organization were in preventing asteroid impacts on Earth. But as we, over the years, have come to realize that really we're part of something even larger. And that is the expansion of humanity into space. Because if you think about where our future lies, where the the next frontier, if you'd like, is, I think I can make a pretty good case, I think others have made this, that the future of humanity in the long term involves us living, working, and operating in places other than just the Earth. If we want to continue to have growth, then the Earth itself has limited resources, energy, and just habitable land. And at some point, if indeed humanity is to continue to grow, then there has to be a place to grow into. And I think we're beginning to be at that stage right now where the cost of doing business in space, the cost of doing operations in space, the cost of launching things off the Earth into space is all dropping to the point where there's beginning to be a virtuous cycle that is changing the equation, if you like, of what it takes to operate in space. And I think we're just at the beginnings of that. And I liken this to other frontiers that have been opened up. If you look back, say, 500 years ago, this is something that was realized by the great nation states at the time, that what they needed to do as they were trying to open up the world was to get accurate maps, charts. And the reason for that is basically three reasons, which can be sort of distilled down to fear, greed, and curiosity, or if you'd like, development, science, and defense. So, I mean, the reason the British, the Spanish, the Portuguese, and sent explorers out around to build maps is so that they could find trade routes, they could find resources, they could defend them if need be, and obviously for curiosity's sake, they brought along, for instance, botanists and biologists and so on often. And those same three reasons led to what the great exploration of the 14th, 15th, 16th centuries. I think if you fast forward even to a few hundred years later, when the United States purchased the Louisiana territories, the very first thing we did is President Jefferson started or put out a new group to be led by Lewis and Clark called the Corps of Discovery, and their job was to map the Louisiana territories, to find trade routes or safe passages, they called it, to see what lived out there, so to bring back samples of plant and animal life, and to find locations which were defensible. And let's fast forward another 100 or so years. In the 1990s, one of the frontiers, it's a virtual frontier now, was genomics. And the very first thing we did, as that field really became important, it became clear how important it was to map the human genome, right? For the same three reasons: protection against diseases, so that's defense, the possible economic benefits of being able to understand the human genome, so there's medicines, and that's a big business. And then, of course, the curiosity aspect of it. Where did human beings come from? How does our genetic makeup work? And so on. And all of this was enabled by having a physical map of the relationship of the various genes and how they interact with each other. So that's been a common driving method towards opening up of new frontiers, and I think we're at the beginnings of that now. So when I look at our solar system right now, which is where we live, and it's where our next frontier is, I think you can make a good case that one of the first things we need to do is map it. Because, as it turns out, we know the locations of the planets pretty well. We know the locations of some of the asteroids pretty well. But pretty much 99% of the asteroids we don't. So much of it is uncharted territory. And if you ask yourself the question, why would we care where all these objects are in the solar system? It's the same three reasons. There's defense. Well, some of those asteroids hit the Earth, as Rusty mentioned. We have seen smaller cases in the last 100 years, 2 cases in the last 100 years of something which has been comparable to the size of a nuclear explosion. And obviously, there's been a history of these throughout planet Earth's history. So there's a defense aspect to it. There is, of course, a monetary aspect of this because trade someday is going to be driven by resources, and development within space is going to be driven by resources within space. And a very good location to get those, particularly water, rock, which can be used to make rocket fuel, is asteroids. I don't know how that's going to happen, but my feeling is that it's going to someday. Obviously, navigation, the asteroids themselves, and the trajectories they're on are going to be a crucial part of understanding how you get around the solar system. It could even be used as navigational aids if you know where they all are. Something like a interplanetary GPS system. If you have a good catalog of where the asteroids are, you can figure out your position. And finally, of course, science, because the evolution of our solar system is written in the dynamical distribution of asteroids as well as their compositions. So for the same three reasons, I think really what we should be thinking of ourselves as doing as we try and protect the Earth from being hit by asteroids is to think of ourselves as mapping the solar system. So let me show you a little bit about what we're doing. This is, if you'd like, a map of the inner solar system, and what we're showing is the propagation of various asteroid orbits. And turns out, as I mentioned before, there's a lot of asteroids which have already been discovered. There's quite a lot of them in the asteroid belt between Mars and Jupiter. And then there's a large number of them, perhaps 1 million or so, that are larger than, say, this room, that are in the inner solar system close to Earth. They're called the near-Earth asteroids. Those are, the majority of those are yet untracked. But when I say tracking and I say building a map, what does that really mean? Well, if you think of building a map like a paper map or the kind of maps they made in the 16th century, they were static, they were flat, they were drawn on a piece of something, parchment or something. But what we're talking about in space is something that's different. First off, maps have changed. They're now more like applications than they are static things. Also, in this case, it's three-dimensional. But there's also another element to it, because each of these objects is moving. So there's actually a time element. If you'd like, each of these maps are now four-dimensional. So you need to know not only where an object is, but where it's going. And so that makes it a four-dimensional map, so it's a little bit different. But when I said that maps are applications, let me use an example of something that I did work on earlier, which was Google Maps. After I left NASA, I did spend some time at NASA at Google helping build Google Maps. And what made Google Maps so revolutionary is that it's an application. It's not static. It can have data added to it. You can query it for answers and results. It has built-in functions, and it's a service, if you'd like. So it's mapping as a service. So the reason that was so revolutionary is it allowed other services to be built on top of it. So for instance, Uber, or Airbnb, or Yelp, or Lyft. These are all companies that built their companies on the Google Maps service. So a modern map, in this case of the solar system, is not just four-dimensional, it's also a service, in the sense that I believe that there are going to be economic applications involved that they can be built off of the map of the solar system, one of which is protecting the Earth from being hit by asteroids. So that itself requires the very precise determination of the trajectories of asteroids. And so what we at the Asteroid Institute are doing is working on calculating these orbits extremely accurately from the types of data which we have, which are in most cases publicly available data sets right now from telescopes around the world. And understanding the uncertainties in these measurements so that we can understand the uncertainties in whether or not something is going to hit the Earth. In other words, the probability that a particular asteroid is going to hit the Earth. And this is an enormous computational challenge because the number of asteroids we're finding is growing exponentially. And it's going to take a big step up in the next few years as, in particular, one very large telescope called the LSST telescope comes online. But there are other proposed telescopes, including space-based, that could further add to this and accelerate this process even more. But with this flood of data, what it takes is a computational system that could sort of continuously update and that can provide these sort of calculations as a background service so that folks who have direct questions such as, is this asteroid going to hit the Earth? And if so, on what date? And if so, where? Those types of questions can be answered. And it's a fun computational challenge. It involves understanding of gravitational mechanics and being able to calculate things. We do include some very esoteric effects besides just the plain old gravity of the sun. Turns out that the other planets affect the orbits of asteroids. In fact, some of the larger asteroids affect the orbits of the smaller asteroids. And even things like the fact that asteroids have not all the same temperature across a single asteroid because they're rotating. Just think of the Earth. The afternoon side is warmer than the morning side. The summer side is warmer than the summer hemisphere is warmer than the winter hemisphere. And if you have a rotating asteroid, they have, even if they may be rotating, not on, faster than once a day, there is still a temperature difference, and that can cause changes in their slight changes, a slight propulsive force that can affect their orbits. Even things like general relativity, Einstein's theory showing that Newton's Newton's understanding of gravity was close but not quite. And we included the fact that the sun's not quite round because the sun is a rotating ball of gas and it's actually slightly elongated. So when you throw all these things in, it becomes very, very interesting and fun computational challenge. But we are in the process at the Asteroid Institute through our ATOM project, which stands for Asteroid Decision and Mapping Project, of building this four-dimensional map. And it's great fun. And I think that if you look forward, run the clock forward, perhaps 10, 20, 30, 40, 50, or even 100 years, as development, economic development happens throughout the solar system, we'll be able to look back. This map is going to be important. These types of services are going to be important to the development of space. And I think, we can protect the Earth because we'll know of impacts before they hit, but I think also we'll be able to do some interesting, we will be able to enable some very, very interesting services to arise in the future. That's all I've got. So, do we do questions now, or do we?
No, well, let me say a few things. We're going to do Q&A. One of the things I didn't say in my introduction is after each of these presentations, we're going to give you guys a chance, unlike the audience tomorrow, which is worldwide, but they don't get a chance to ask questions. You guys do. So any questions after these presentations will be available. One thing I was going to say in introducing Ed and forgot was that thinking about the timing of some of these things, I realized as I was just looking up facts about Ed that he was all of 5 months old when I was selected as an astronaut. So just to give some perspective on what
Kids
goes on
these
here.
days. Huh?
So in any event, we'll take about 10 minutes for any individual questions you might want to have. Yeah, just go ahead.
So, Ed, is this map, this asteroid map you're developing in this ADEM program, is it going to be published publicly? Is it plans to be made publicly available, like Google Earth Map?
Let me ask something. Could you hear the question in the back? So why don't you repeat it, Ed?
Okay, so the question, I guess, is access to this map going to be publicly available? And yes, in the sense that, let's go back to the example of Google Maps. They do have, their services are available to be developed on top of, and I think that's important because there are going to be specialized use cases, and we don't want to develop them all. We want the service to be extensible. So, for instance, others can add data to the map, as if folks have specialized observations on, say, composition or spectra, resources and so on, those can be added to a map as metadata. So just exactly like Google Maps allows people to label their business or whatnot. Those types of things need to be available for it to really have maximal usage.
Which institution is it? Your foundation, who is building this application? Has it been built? Is it
We are working on it. Much of it is open source, but we have open programming interfaces. They're called APIs that allow data flow in and out. So, for instance, if you want to query the system to get the orbit of a particular object, for instance, that there's an open published standard that we're working on. So right now it is not fully available publicly because it's still in the internal usage state, and many of the tools are still being built. We are currently 100% privately financed by donations. So this is a project which is done by private donors, and but we do believe that this is first off, we're going to open it up as the services become more stable, as the versions become more mature. This is a project of the Asteroid Institute. The Asteroid Institute itself is a project of the B612 Foundation. So yes.
Yeah, other questions? Yes.
Yeah, what's the target in terms of the size of this map? Are you going further away than just the asteroid belt between Mars?
The question is, what's the target of this? You asked if it's further away than the asteroid belt. I think the better way to think of it is to think of it is in terms of the size of objects that we're trying to catalog. Right now, what's publicly available of information of the asteroids are cataloged down. It's probably complete down to about 800 meters or so, roughly. 800 meters is still a fairly large asteroid. It's pretty much accepted that at 1 kilometer, just a little bit larger, should one of those hit the Earth, that's likely the end of human civilization. That's not something that's going to sterilize the Earth or kill most of the species, but human civilization may or may not survive that. So smaller than that, the map is still incomplete. Now, the planned telescopes over the next few years hope to make this map complete down to sizes of asteroids approximately 100 to 200 meters, somewhere's in there. And that size asteroid is still of extraordinarily destructive capability should they hit the Earth, and something like 100 megatons of TNT, which is far and away larger than any operational nuclear warhead that is currently deployed, far and away. We believe that it needs to be brought down to even smaller sizes, at least for the purposes of protecting the planet. And that recommendation is also part of some of the U.S. government recommendations currently. Although there isn't yet deployed technology capable of tracking all of those asteroids, we think that there are some interesting, promising technical areas that we've been developing that could, in fact, take the surveys down that far. So,
and let me just add to that again, the initial interests of B612 Foundation and therefore, to some extent, the origins of the Asteroid Institute were planetary defense. And so the natural thing to look at, including in the totality of asteroid populations, is the near-Earth asteroid population. That is, the ones that can impact the Earth, depending on phasing and that sort of thing. It happens that when you look at asteroids from the standpoint of resource, they're also the ones that are easier to get to, the ones out in the main asteroid belt. While there are many, many more of them, they're a little more expensive to get to. Now, eventually, Ed's work may end up including a map of the main asteroid belt, but certainly the initial and most interesting work to most people is going to be the near-Earth asteroid population, which are the ones that also have the potential for impact.
Yeah, the first areas you map are the areas closest to home.
Yeah, right,
And
right,
so-
exactly. Yes, Richard.
What's the margin of error in predicting the future trajectory of an asteroid as you go out 10 years, 100 years, and so on?
2.5.
Yeah, the question is, what's the margin of error as you go out further in time, predicting the location of an asteroid? Obviously, as you mentioned, it's a function of how much further in the future you're trying to get to. And it's a function of how many observations you've managed to take of that particular asteroid. The more times you see it over the longer period of time, the better you can fit an orbit to it to be consistent with all those observations. So it's not a simple answer because it depends upon the exact geometry and the particular orbit and so on. But in order to, for instance, ascertain whether an asteroid is going to hit the Earth or not, you typically have to have an asteroid, the uncertainty in position of less than the size of the Earth, right? And if your uncertainty is larger than the size of the Earth, then you can't say for sure whether that asteroid is going to hit the Earth or not. You can only state with some probability, right? So the goal of these observations is to bring the uncertainties down to within the size of the Earth.
With enough time to do
With
something
enough
about
time,
it.
yes. And that turns out to be one of the original driving projects that we're using to drive development of our map, is that we are actually calculating asteroid impact probabilities and looking at how many observations it takes on average across asteroids that are likely to hit the Earth. It takes in order to get the uncertainty down to within a few thousand miles. And we're finding some interesting things which we're going to report about within the next, hopefully, few months. But
Richard, let me just add to that. One thing that's interesting is that what's most important is observations over a long period of time. That is, a whole bunch of observations of an asteroid over a short period, a short portion of its arc, is not particularly useful compared with 2 orbits later, picking it up again and seeing where it is. So observations over an extended period, where it's gone around the sun a few times, is where you really shrink the uncertainty much more dramatically. So a lot of observations over a short period makes not all that much difference. Let me get the question here.
Mm-hmm.
What about the nasty one that's sitting around in the Oort cloud and gets kicked out by a big one and comes straight in on a very parabolic orbit towards the Earth?
yeah, this is a question essentially about comets. And what about those things that are not orbiting, near the Earth, but instead sit very far out, even past the orbit of Pluto, and that might sort of occasionally get bumped around a little bit and suddenly come careening into the inner solar system. These are comets. And there isn't much we can do about them currently because you don't get much warning, as you say, and they tend to come in very, very fast because they're dropping, essentially falling in towards the sun from great distances. They pick up a lot of speed. And so you don't have a lot of time to sort of figure out what to do. Now, the lucky part of this is that those types of objects are outnumbered by the asteroids by nearly 10,000 to 1. So it is an issue that we do not yet have the technology to really map those objects accurately out there. But I don't think that should stop us from, addressing the 10,000 times more likely objects, which are those in the inner solar system.
In the back? Yes, ma'am.
The staffing exercise of the asteroids, what other characteristics are you also envisaging, including when classifying them, besides size, I don't know, up to what extent composition, shape, speed, and
Yeah, the question is, what other things might you wish to tag an asteroid with besides just its size and its orbit or composition? And eventually, I could see that you would tag asteroids with other things, such as ownership. such as who has mineral rights there, such as, you know, who's doing business there, who is, those types of things will eventually happen. But I think, as you state correctly right now, the things you want to start with are size, composition, or at least spectral type. But eventually, I think some of these, as these objects are visited and more is known about them, other pieces of information will be added to them.
Is there an Airbnb facility there? Yeah. Or maybe a space B&B?
Is there a good coffee shop near it?
There was one other question. Where was that? Yes.
In fact, my predecessor had the same question as I had, but maybe I'd like to add on that. You are doing this, of course, in the framework of asteroid day, asteroid institute. But if you are looking to what maybe Luxembourg is doing with space resources / asteroids, is there a kind of cooperation that you are entertaining with the space resources community, or is this let's say, a kind of silo where you're not talking to the other interested people in asteroids?
The question is this something that we're just doing it by ourselves, or are we interested in cooperation with others, like Luxembourg, for instance? Okay, and I would say that we're definitely interested in cooperating with others because, again, the map itself will be useful for many things. Economic development in particular, I think, being an important driver of future developments, you know, of future space technology. And so, you know, we're definitely interested in talking to others about potential uses of the map or potentially being involved in our project.
You really can't do any development anywhere without a map. That's number one. That helps everybody from science to economic development to planetary protection. So the map is the base, dynamic map is really the basis, which is of foundational use for just about everything else that you want to do if you want to do something with asteroids.
So I'll throw something out here that this could be the basis of a very, very nice international collaborative project.
Okay, well, thank you very much, and we're going to have a lot of time for questions here. I'd like to move on to the second presentation. Let me just say before I leave Ed, I should have said it earlier, Ed was an astronaut as well as myself and Doran, the other one, three of us up here. Ed flew 3 times, twice on the space shuttle and once on the space station, so you want to know something about that, pin him down in the reception or whatever. And I'll go ahead and introduce Mark Boslough here on my right. Mark is a physicist out of Caltech who worked for years at the Sandia Laboratories in New Mexico. And Mark is a unique individual in my book, anyway. Some people are ambulance chasers, you know, and they make money from that. Lawyers, I think, they're called the general category. Hold on, I got to hit my watch here. Mark is an asteroid chaser, and in particular, asteroids that have crashed to Earth. Stop. And Mark disappeared from the United States within a matter of 24 hours or 36 hours after the Chelyabinsk object hit back in 2013. So Mark is really, I would say, just about the world's expert in terms of the field operation of asteroids impacting the surface of the Earth. And Mark, though, being a very broad person, thinks in very broad terms. And one of the things Mark has done is looked at the future of near-Earth objects and how does this play out in terms of the general public and business or whatever. And so Mark is going to present a new business plan for near-Earth objects.
Thank you, Rusty. Oh, yeah. Thank you, Rusty. Is this on? Can you hear me? First, I'd like to start by thanking you for the invitation. It's a pleasure to be back in Luxembourg after a year. We really enjoyed it last year, the beauty and the hospitality of this part of Europe. And so we're really enjoying ourselves already. So based on what Rusty and Ed both said, I think we're all thinking along the same lines. And I am thinking about the future, a future in which we have discovered everything that could potentially be catastrophic, that could wipe out the planet, wipe out civilization, wipe out a continent. Anything of that size, we will have discovered. If it is on a collision course, we will have taken care of it. If it's not on a collision course, we don't have to worry about it, but we do still have to monitor it, as Rusty and Ed talked about in response to one of the questions. We can't just forget about them. In fact, we will have the map, a big list, a big table of all the asteroids we've discovered, their characteristics, and there will be tens of thousands or more asteroids on that list, near-Earth asteroids on that list. We will pass that along to the next generation, and they will continue, you know, it will be their job from then on. But there are asteroids below a certain size that we won't have on the list. The Chelyabinsk-sized objects, there are something like 10 million of those. Unless we build just a fantastic number of space telescopes and put them in unusual orbits and continue to track those and continue to track anything that's passing through the inner solar system at all, we're not going to find all of those. And in a way, we shouldn't expect to. I think that is beyond the scope of planetary defense, because objects of that size, if we can find those as they're on their final approach, what some of us call death plunge, that means death of the asteroid, not death of the people in its path, because with sufficient notice, we can get people out of the way, or we can get them to shelter in place. That makes the most sense for objects of the size of the Chelyabinsk impactor. So I'm going to start with a philosophical question. So the question is, if an asteroid falls and nobody is there to see it, does it still look cool? And my answer is, this should never happen. We should always find the big, reasonably big Chelyabinsk-sized objects, and even much smaller objects, which would be fantastic from the point of view of getting to witness it. So there's the curiosity part, and also the greed part of the triad of curiosity, greed, and fear. These small ones aren't dangerous. They're not going to be dangerous to people under their path, but they're going to be fantastic to see, feeding people's curiosity. They're going to drop meteorites. Many will drop meteorites on land. That feeds the curiosity of science. And they can be exploited for commercial gain, such as flying missions, tourists, or scientists, or both, to watch these kinds of events happen. So there are a lot of these events. There's a lot of data on what we call bolides, large fireballs, large meteors that streak across the sky, but the ones that explode with energies of this scale of nuclear, small nuclear explosions or bigger. And this is a map of the last, 25 years or so of events like this. The big one, you can see a very big one. I need to point up here where you can see. That's Chelyabinsk right there. Now this is a logarithmic scale, so the dot area is not proportional to the amount of energy released. Here's a scale of energy. There's lots of little bitty ones. So there's a distribution, a size distribution of this, a power law distribution where most of the energy is in the biggest ones. And in fact, the energy that was released by Chelyabinsk, almost half a megaton, is almost as big as all the energy released in all of these other ones put together. Now, I downloaded this yesterday. There's already been 2 events this month. There's been 20 so far this year. And since I downloaded this, I looked again yesterday, or I looked again this morning, and there's actually a new one. There was an event over Libya 2 days ago that released something like 1/10 of a kiloton of energy. So if you can imagine, 20 or 40 of these events happening a year that are discovered in advance, there really is a lot of opportunity with sufficient warning to send a mission, to send space tourists, entry-level space tourists, adventure tourists, as well as scientists with instrumentation on an airplane, or even to put instruments on the ground and track these things as they enter the atmosphere, to understand the physics, better understand the physics, thank you, as well as possibly follow the meteorites in their dark flight after they stop glowing all the way to the ground and immediately go there and pick them up.
Pull out at the last minute.
Yeah. So this is one of, I think, 2 graphs I'm going to show.
Sorry, it's a pilot.
So this is a whole lot of data based in part on that bolide map. And the green dots here are the bolides. That's the bolide flux. And so this is this power law distribution. We have a couple of big observations. These 3 were all observed. I drew an arrow down to where we think the probability actually is for these events, but this is what you would calculate if you just took the window of opportunity to observe such a thing and observed one this size or bigger, as is the case for Tunguska. So what this implies is that both Tunguska and Chelyabinsk, this refers to Chelyabinsk here, are outliers. I'm sorry, this is Chelyabinsk here. There was actually a bigger one that was observed in 1963 through infrasound using very low frequency sound waves, which are part of the global monitoring system looking for clandestine nuclear explosions in violation of our treaties. So I've put some bars on here just to sort of give you an estimate of how frequently these events are. So this is my estimate of Tunguska, about a 40 meter diameter object that exploded with an energy of about 5 megatons over Siberia in 1908. That's about a 500-year event, once in 500 years. These are rough estimates. There's some uncertainty. It could be once in 1,000 years. Others estimate even longer intervals. In any way you look at it, that is an unusual event. Chelyabinsk, which happened 5 years ago, that's a once in 50-year event. So we were very lucky to get to see that. Chelyabinsk wasn't lucky to have all those broken windows and injuries, but from a scientific perspective, we were lucky that it happened in a place where there were a lot of dash cams and phone videos that my colleagues got to analyze and determine what the yield was and the trajectory was and so forth. This is a 4-meter asteroid, roughly 5 kilotons. There's not a one-to-one correspondence because that also depends on density, it also depends on velocity, and those things vary. Now, the first death plunge object, the first object that was observed before impact happened in October of 2008, 10 years ago, 2008 TC3. And it was discovered by the Catalina Sky Survey, Richard Kowalski, and there were follow-up observations, and there were enough follow-up observations and enough time for other telescopes to nail down the trajectory that it was predicted to impact, and the prediction was accurate to within a second and within about 1 kilometer of the point of impact in northern Sudan. Unfortunately, there was really nobody there to that was ready with a camera or instrumentation, but this very much inspired me. And in fact, I found out about it after it was announced that this was going to be an impact, and I tried calling everybody I could that knew somebody in the in Egypt, in southern Egypt, in places that would be near enough to actually record something, and I was unable to do that, which was very frustrating to me. This is a 2-meter asteroid, and this is very close to the size of the one that impacted in Botswana this month. So this is the third such event of an object that was discovered on a collision course. This was only discovered 6 hours or so before impact, and there weren't enough follow-up observations to determine for sure if it would hit, and if so, where it would hit, but nevertheless it did hit, and it hit right precisely at the time that it was supposed to hit, if it hit where it did. So I can come back to that. But that's a once in a month, roughly, a once in a month event. So you can imagine.
If you didn't get it, Mark is a nerd.
If you, I fully admit that. I own that one. Okay, so that's one that if we could make this a routine discovery, these would be happening, you know, almost monthly. Of course, only half of those would be on the night side and coming from the night sky to be discovered in advance, so we might get one every couple of months. Now that one was discovered by Richard Kowalski of the Catalina Sky Survey as well. And in between those two, there was an object called 2014 AA. That one, there was no follow-up. It was actually discovered on New Year's Eve in Arizona time zone. It was actually on January 1st, Universal Time. That was discovered by Richard Kowalski of the Catalina Sky Survey. So he does something that nobody else does, apparently, and we need to figure out what that is. Now this is, I won't go into detail on this graph, but this is the way we calculate risk or estimate risk. And we've got a kill curve, so this is the estimated number of people that would die in millions from an event, the impact of an object of this size. So this is above the global catastrophe threshold. We're getting up into the range of the population of the entire planet. But we've discovered most of the ones less than a kilometer, or I'm sorry, greater than a kilometer, so most of the risk now is dominated by objects less than a kilometer that are not going to kill everyone. So this is a probability distribution curve. And if you multiply these two together, you get this cyan curve, and if you take the area under that, that is the number of fatalities expected per year in the long run, averaged over many, many years, given the distribution of known asteroids. Now, I'm calculating this assuming we've discovered 90% of objects greater than 140 meters in diameter, which is the current mandate. So in this case, most of the risk now, once we complete that, most of the risk will be due to these very small death plunge objects. Therefore, we should be shifting our attention to those once we complete Ed's map. So this is just a poster that I presented where when I realized, you know, we really need to think about the future because we have been so successful at discovering these, and we are accelerating and enhancing our observational survey capability, that we're going to get on the part of the steep part of the discovery curve, and we're going to start discovering these at a very fast rate. Do I only have 2 minutes left? Okay.
No, you got, I'm sorry. I'm sorry. You got 6 minutes.
Okay. Okay. So I attended a long program in Munich that was dedicated to studies of near-Earth objects from a science, but also from a commercial and a risk perspective. Alan was there as well. And after we eliminate the large ones that are potentially catastrophic, we don't know how soon that'll be, and we may disagree on when that is. But there's still sustainable planetary defense to be done. As I mentioned earlier, there's the ongoing short warning surveys that we need to keep doing because these are going to continue to come out of the blue, just like Chelyabinsk, just like 2008 TC3. There's going to be civil defense and planning. We need to really understand the effects of these. So the ones that are small and we don't have enough time to deflect or destroy, we can get people out of the way, we can get them underground, we can make sure they know to stay away from windows, things like that. And there's the ongoing monitoring of potentially hazardous objects, which we discussed earlier. They all have uncertainty, so when we extrapolate the orbits out into the future, the orbit we calculate is going to diverge from the actual orbit just due to the initial uncertainty, and sometimes that's nonlinear for ones that pass close to a planet. And after that, if there's a little bit of uncertainty, it turns into a big uncertainty. Now, the second part of that is the greed, fear, and curiosity part, and I chose to completely think out of the box. We're kind of in brainstorming mode here. People have talked about mining asteroids for precious metals, for gold or platinum or so forth, but I think of them more as quarries and gravel pits. The mass in space for radiation shielding, for extraction of construction materials, for space structures, that's much more important in my mind and more valuable than mining precious metals to bring to Earth for things like jewelry. We can think of radiation shielding for Earth-Mars transfer orbits. Can we deflect asteroids that happen to be passing by the Earth and have an aphelion near Mars? Can we deflect those into an orbit where we can launch astronauts to hide behind the asteroid or burrow into the asteroid or use that asteroid's resources for the 8 months or so to get to Mars? So we don't have to launch all that mass. Can we harden current commercial satellites or geolocation satellites so that they're not susceptible to a cascade of orbital debris or attack? Can we use plumes from airbursts, intentional airbursts, to sweep low Earth orbiting debris out of low Earth orbit? Can we use them for geoengineering Earth or terraforming Mars? I'm not advocating either of these. This is brainstorming. And then, as I mentioned, entry-level space tourism and science. And Ed mentioned genomics, and maybe we could think of something along the lines of neomics, which is a large data, big data problem, and an informatics problem. I'm very interested in validating my models. This is my model for the airburst over Tunguska, an explosion about 12 kilometers above the surface, and a shock wave passing along the ground. This is the vertical map view of that, showing the intensity of the sound wave, the blast wave across the surface. And the map that I constructed from that, and similar maps that I constructed by varying parameters. Can we do observations on the ground from a pre-discovered death plunge object that allows us to validate these types of calculations? We can only use the map of tree fall at Tunguska to do that now. Here's a missed opportunity. If we'd have seen this one coming, we'd have more than large booms, and Russian profanity to go on. And I'll go ahead before I play that part. This is my simulation showing, which wasn't hard to do, that in part explains why there were two trails. This is looking down the wake, and there's a buoyant plume that rises very much like a mushroom cloud and splits into two contrail-looking wakes. So I wrote this up for Astronomy Magazine, my idea of deploying instruments. Am I out of time? 1 minute. Okay. Based on that article in Astronomy Magazine, which you can find online, there is an IMAX film in production, and I just received this from the producer of that, showing a notional sensor package that could be deployed in the path of such an event. And here is my big explosion that's going to be featured on that IMAX movie. This is actually something like a 270 meter diameter asteroid, a huge explosion, sending debris up into space. And I think Rusty's going to give me a 0 here, so I will stop with this.
Okay, Mark, thank you very much. I think all of you can now begin to appreciate why Mark is one of my favorite people in this game. He's always thinking out of the box. One never knows what box it is he's thinking out of, but it's always fun and innovative and informative. So with that, I assume there'd be a number of questions, so let's shoot. Richard?
In your graph of human deaths against size, the green curve was obviously two curves. There was clearly it was a very odd-shaped green curve.
Right.
And it looks as though there are two populations of asteroids.
It,
Didn't explain that.
so, yeah, so the green curve does not reflect populations of asteroids. It reflects the effects of asteroids. And of course, we have no way of validating this. This is mostly based on theory, but there is, but below that inflection point, so as you look to the left on that graph, that's based on people being killed by the event itself and the immediate effects of the impact, the blast wave, the debris, the thermal effects. And above that cusp is the follow-on effect, the effects on the Earth, the change of climate, the global wildfires, and the subsequent collapse of agriculture and even civilization. So the expected deaths to the right, to the large side of that curve, are really the catastrophe and the continuing catastrophe without end of an event of that size.
There's even a dip at the inflection point.
There shouldn't be, and that may be a plotting issue. I don't know how that. Yeah, that shouldn't be there.
You shouldn't wish for that notch, Richard.
Yeah, so that's the number of deaths. It's a graph of the number of expected deaths at a given, for an event of a given magnitude. But of course, one kilometer impact event is not the same as another one. One could hit in the Gulf of Mexico, and one could hit, on the Antarctic ice sheet, and those would have very different effects.
Other questions? Yes.
Thank you for your very interesting presentation. You briefly also mentioned the problematic of space debris, and that remembers me, I assisted at a presentation from ESA about the problematic of space debris and the deep impact space debris can have, especially on commercial satellites, but also on space vessels flying out there on missions. For example, I guess it was 2 or 3 years ago, the crew of ISS had to refuge in the Soyuz capsule in order to have rescue escape if they got hit by larger space debris that had not been monitored timely. So in your program, do you also try to monitor space debris or small asteroids that are not even much larger than space debris in order to protect commercial activities, commercial satellites flying out there, and how do you intend to do this?
So the question was about space debris, particularly as it puts commercial satellites and the space station in low Earth orbit at risk. And I think the question was, are we monitoring that, and what is being done about that? And I'm not involved. There are people monitoring that and very concerned with that because it's an extraordinary risk and concern. But that, in a sense, is outside the scope of near-Earth objects and asteroids. But when I made that list of potential things that our community could be working on, it does overlap with the space debris problem. And I have one of these wacky out-of-the-box ideas that, like Tunguska and Shoemaker-Levy 9, the comet that hit Jupiter, any asteroid that enters the Earth's atmosphere, if the asteroid is Chelyabinsk or Tunguska-sized, will create a plume. Will create a plume of vaporized asteroid and atmosphere at high pressure that is ejected to altitudes of low Earth orbit. And if it happened by accident, when valuable asteroids or valuable satellites were flying over it, it could cause those satellites to re-enter or be damaged. But if you did something like that intentionally, in the event that space debris completely gets out of control and you have to sweep it up, that's one potential way to do it. And like I said, it's a very extreme, out-of-the-box idea.
I should mention that the mathematics and physics of understanding and calculating orbits is very similar between space debris, which is orbiting Earth, versus the asteroid problem or near-Earth objects, which are orbiting the sun. But there is a connection in terms that there are people who work on both problems, including myself, because of the computational similarity in the way you calculate orbits and predict collisions.
But let me say that the economic threat to orbital assets, satellites of all kinds, GPS, communication, whatever, the threat there is much, much higher from orbital debris than it is from asteroids coming through in a transient way. Nevertheless, it does happen, and when I was outside, for example, on Apollo 9, my visor ended up with little bitty dings. Every space shuttle that flew ended up with little pits in the windshield. So the threat is real, but the frequency of very, very small things, which will make those kinds of pits, is much higher than the kind of thing which is going to create a catastrophe for the ISS or for your satellite. So space debris is a much, much more real and a much more difficult problem in some sense to cure than worrying about asteroids hitting your satellite. Yeah.
In light of the Chelyabinsk events, would you consider implementing a strategy for social media in order to track such events better?
Absolutely. In fact, I found out about Chelyabinsk on social media.
As did NASA.
I'm sorry?
As did NASA.
Yeah. Okay.
That is actually true.
Yeah. I was fortunate to find out about it within a couple hours of when it happened, because I was giving a presentation the following day, and just before I went to bed, I finished my presentation. This was on Valentine's Day, but and I was single. But anyway, so I finished my presentation. I went on Facebook, and at the very top, some Canadian Facebook friend had just posted an article, a link to a Russian article with a YouTube video, and it said a UFO explodes over Chelyabinsk. And he posted it because he stayed up late at night to play Russian computer chess with Russian friends. And so that's how it got to me. And I immediately started, trying to get my colleagues' attention, and it was too late in most of Europe and the east coast of the US, so I really didn't get too much attention. So we didn't find out really until the next day how big and how real it was. But I did look at the YouTube video, and it was very clear to me what had happened. So I would absolutely advocate for apps, in fact, that people can download so that they get warnings very quickly. And there's no reason we can't do that, because NASA and ESA are dedicated to being very transparent about all the data, and when they call for follow-up on something, it would be very good for people to know about it. And in fact, this event that happened on June 2nd, I was with a lot of key people in a beer garden at the bottom of the Ries impact crater in Bavaria, when several people's phones got their alerts. And they immediately went to business, but because we were at the bottom of craters, some of them had to drive up to the rim so that they could get their data going so they could send email and call for follow-ups on this event. At the time it was first announced, it only had a 5% estimated probability of impact. But if all that information had gone out onto some kind of app where individuals could be alerted, then third parties could start calculating impact corridors across the Earth and then start calling for observations. And in fact, such an app could have a built-in fireball, video camera that has geolocation and everything else. That would be invaluable. So that would be a really good way to implement this whole instrumented depth plunge idea, but in a crowdsourced way.
Well, that takes us just about to the point of a break, but let's see if there's one more question that we can take. There's a couple. Let's go to the gentleman there and then two. You white hair. Yes, you, sir.
I'm sorry, my hearing isn't.
Lightning strike deaths, where does it stand currently?
Lightning strike deaths. How does this compare? So this is my number. This 36 deaths per year is the number once this current survey mandate is complete. That's my estimate. I don't know what lightning. Do you know what? It's. Ed says orders of magnitude higher, and I sort of agree with that. It's probably much higher.
Remember that this is pure fiction in the sense that this is an average over 100 million years, okay? So these deaths occur in either 0, as in most cases, most years, it's 0, 0, 0, 0, 0, 0, and then 1 million. So it's a very different, average numbers are not the way to think of a problem like that, okay?
Well,
it's a very poor proxy.
Let's just take the last question and then we'll have a break. Yes.
Do you have some work on to complement the time return versus the size? Are you working also on geological data, sedimentological data with some people?
I'm sorry, on what kind of data?
In the sedimentary archive in geology, to complement your time return period versus the size. Do you have some work or any people working on that?
Okay, so the question is about geologic data. I assume you mean on impact craters in the geologic record, like the.
Or sedimental, tsunamis, any other records in sedimentological way.
Okay. So geologic data, so the question is, do I work on geologic data, including tsunami and other evidence for impact? And I have done some work. I've done some analysis of shocked minerals in the Coconino Sandstone at Meteor Crater, Arizona, and also Libyan desert glass, which appears to be an airburst formed enigmatic glass that's found in the Sahara Desert. It's beautiful.
But the answer is that our field of activity pays very close attention to geologic analysis, and this is integrated in our work that's reported by JPL and others around the world. So yes, we're in very direct contact with that community. So, and catch us during the break if you want, and ask further questions. We'll take a break now for 10 minutes. Please be back in your seats, and we'll start up again.
And for anyone who wants to know where the restrooms are, they're down the door here, down 2 floors. Just follow the signs. It's kind of confusing.
That's right, yeah. We had so much fun last year. All right.
talk. My name's Alexander. I work at Deep Space Industries.
Ah, okay. Oh, you're part of the new group that's
coming here slowly.
How many folks do you have on your team?
Well, there's 2 on payroll, so it's not exactly a huge engineering team. We're still working with government to try and work out what it is we're doing here and how we can divide our activities between California and here in an urgent fashion. But we're very interested in this map, or this application of yours. Have you spoken with any of our
Not really so much about this. You should think of this at the moment as being a development project.
Yeah.
I mean, we're gathering resources, we're getting some of the
Well, the distance
probability calculations are being run in the cloud. So all of these things are all sort of being put together. Don't think that
I imagine it's not a trivial case, but
right. Hundreds of engineers over decades.
Yeah, if the Earth did not have an atmosphere,
Nice to see you again.
That's good. So, we're not in that state.
okay.
How's it going? Hi. You guys came all the way from San Francisco. Good progress.
No, in the long term, of course, something like this will be instrumental for our purposes. But even in the short term, with our mission planning now, we do use resources.
There's large uncertainties and you need to track those uncertainties. They're very large.
a little bit of bureaucracy to do this morning. Since I own an apartment, so it's a little late.
Nowhere near because the uncertainties are so large that they could be anywhere on the world.
Yeah, no, we have this is actually one of our biggest downsides is the orbital condition code on the asteroids we do have. It's like great asteroid. I don't know where it is.
How are you propagating your orbit?
Well, we're not at the moment. Or rather, that we are, but we're not doing anything clever. We're just using taking the TLEs from data sources and then the SDK or something.
Wait.
So it's quite
TLEs for TLEs for.
Or the equivalent. So you get the orbital parameters
Orbital
at any given moment.
You can expect to be off by millions of miles.
Yeah, that's what we're expecting. And we can accept numbers probably a million miles.
No, you're probably off in tens of millions of miles.
Yeah. I mean, there's a threshold where we can accept. That's how absurd. But when we start
like the
approaching.
whole transportation.
But yeah, we're trying to narrow it down. But the point I'm trying to make is that when you guys have this map.
Well, we're releasing bits and pieces of it. You know, we've got people already that are using bits and pieces of our code. Our propagator, for instance, we've shown that us and JPL agree on a propagator within sort of, if you take sort of about 10, 20, 30 years, you know, we're within a few tens of meters of each other, so we can do it as well as JPL. But the issue is really more with the observations. Most of these asteroids have too infrequent of observations that the parameters.
But as long as you sort of understand how inaccurate things are, that's already a pretty good starting point.
Yeah,
exactly.
Something out there. The problem is that
roughly somewhere.
Yeah, and the problem is that what you get off of JPL doesn't have the full orbit, doesn't have the full covariance matrix.
Yeah.
So we're providing some of those things.
Yeah. Well, that's interesting work. Will it be sort of widely announced, or is it sort of released quietly? Should I?
No, I mean, we haven't really thought at all about it. We're probably going to announce Foundation.org.
Oh, that's easy enough.
Do you have a card?
Or I can
Edit bcsfoundation.org.
Yeah. Well, yeah. I mean, obviously, your approach is a little different from ours, but we're very interested in your work, and we'd like to mention your background. I'm an electrical engineer, so I'm all the way from dynamics and time selection, but nonetheless, we're a small company.
And what are you working on? What's the idea out here?
So,
because I know it's one of the requirements of Luxembourg.
yeah, so we're working out a little bit what we're going to do. At the moment, we're doing the power systems. Largely because that was something that's relatively easy to carve off and ship out here and develop and ship back. We want to do more. We're talking about large-scale manufacturing and propulsion systems.
What's the first flight that you guys want to take?
So our first asteroid mission would be in 2020. But before that, we're likely to fly.
We're a little oversold at this point. I don't know what the
We're building
reconciliation
an asteroid
was.
probe system, but we're also
I know, that was 3 days ago. All of us.
He just sent me a thing now saying, did you see that? So we want to create a satellite bus that goes into space to provide low-cost access to deep space sources. And we'll use them for going to asteroids, but other people might use them for small scale.
So the business model currently is
So I think the answer is, I don't know right now, because we, this morning when we woke up, all the comments back were like 185. And,
You've got a whole,
145.
when people realize you can build something.
But then again, we have so many notions here. It's like I don't even exactly know how to.
Useful. We want to do something the same.
Oh, really? Is it?
Deep space. I think there are a lot of people, PIs, universities, research organizations, perhaps.
Yeah, you got to be careful of them as customers because they tend to be starved for cash.
Yes, yeah. We're not quite sure how it works, but
that isn't necessarily who you want as your product customers.
no, we're working out how that works. But we're hoping that the value proposition of a $10 million delivery mission versus waiting for getting on 1 billion NASA missions.
When you were your first on space?
The first flight was in 1997.
And that was Apollo, and that was space shuttle.
Space shuttle.
Apollo was
Finished in 1972. So I'm much younger than the rest of you.
Which of the upcoming spacecraft